Okay, and to finish up Chapter 3, we have present value, section 3.4. And so here we'll start again with the formula for present value and explain a little bit what it is. And then there's some problems that deal with just doing computations with the formula. Let's just make sure my pen is working here. And some word problems, actually a whole bunch of them. And some amortization problems, which apparently I put in twice. And then some problems tying present and future value together. And then a brief guide about telling finance problems apart and a bonus video that drives the formula for the present value. So, what's the present value formula? Present value then is used when you get the money in the present and you have to pay it back. Technically, you're paying money out of an account that exists, as opposed to future value, we're paying money into an account. So, but usually the classic example here is a mortgage, where you borrow money from the bank and then you pay it back, and you pay it back in a stream of monthly payments. So future value and present value are the same in that there's a sequence of payments you're making, monthly payments, weekly payments, whatever. The difference is, when do you get the money? Do you have the money in the beginning, and that would be present value, or do you get the money at the end, and that's future value? The interest problems, compound interest, continuously compound interest, simple interest, those involve a lump sum, no stream of payments there. Anyway, this is the present value formula. PV equals payment, 1 minus 1 plus I to the minus n over I. All the variables are the same except PV. This is the problem with cut and paste. Present value, or the amount in the account in the present. Right? It's how much you borrow. PMT is the payments. I is the interest per period, so R over M again. N is the number of compounding periods. N equals MT. Right? So M times a year times T years. You don't need to memorize the formula again, because it'll be given to you on tests and quizzes in the final, but you do need to know what the variables stand for. Problems involving I and N, so problems 1, 3, 5, 7 in section 3.4, these are just like the problems in section 3.3, so we won't go through those. Problems involving the present value formula, so 9, 11, 13, 18, they pretty much run like this. If present value is 40,000, I is 0.01, and N equals 60, what is the payment? How much interest is paid? So what do we have here? Present value is $40,000, so somebody's borrowed $40,000. They have to pay it back. They pay 1% interest every period. So if we're talking about, say, something happening monthly, we're talking about a 12% annual rate. And it's paid off in 60 equal payments. And then again, if this was done monthly, then that's 5 years, because 60 divided by 12 is 5. So how big is each payment and how much interest is paid? So we write down the formula. Present value equals payment 1 minus 1 plus I to the minus N over I, payment, and present value, payment, I, and always write down your variables so you know which ones you're looking for and which ones you got. So present value, they tell you is 40,000. I, they tell you is 0.01, and they tell you is 60, and they want to know what the payment is. So you plug everything in. 40,000 equals a payment, which you do not know. 1 minus 1 plus 0.01 raised to the minus 60th over 0.01. And if you grind that out, the payment is, well, you have to calculate this fraction, divide 40,000 by it, and you get the payment to be $889.78. So, how much did you pay in interest? Well, your total payments, right? How much did you pay total? Well, you made 60 payments of $889.78. So your total payments were $53,386.67. How much did you borrow? I usually think of present value as how much I'm borrowing. Well, I borrowed 40,000, right? That's my present value. So this is how much you paid, this is how much you borrowed. How much did you pay in interest? Well, that's the difference. This number minus this number, 13,386.67. So how much you paid total minus how much you borrowed, that's how much interest you paid. So, no word problems. Here we go. Here's a classic word problem. A couple buy a house for $175,000. They pay 20% down and take out a 30-year mortgage for the rest. The mortgage has 2% annual interest compounded monthly. What's their monthly payment and how much do they pay in interest? So, how much do they actually borrow? That's the first thing. So they pay 20% down. How much do they pay? Well, 0.2 times 175,000, and that is a 1. So their down payment is $35,000. So they have to borrow $140,000, right? Because the whole house costs $175,000, they pay $35,000, so they have to borrow the rest, which is $140,000. So PV equals, that's how much they borrow from the bank. Payment, we don't know what that is. Oh, but we do know what the formula is. PV equals payment, big fraction, I on the bottom. This one's got 1 minus 1 plus I to the minus n on the top. I'll scroll that up a little bit. Payment equals, we don't know. I, 2% annual interest compounded monthly, so 0.02 over 12, which is 0.0166 dot dot dot, and n is how many payments they make. 12 payments a year for 30 years, 360 payments. Okay, so plug everything in. 140,000 equals payment 1 minus 1 plus 0.0166 dot dot to the minus 360 over 0.0166 dot dot dot. And grind that out. Right, figure out what this fraction is. Divide 140,000 by the fraction, you get the payment is $517.47. Great. So, how much is the total that they paid to repay the mortgage? Well, 517.47, that's how big each monthly payment was, times 360, that's how many payments they made. And so the total payments are $186,288.21. The mortgage was $140,000 that they borrowed. How much did they pay in interest? Well, the interest is this minus that. It's the total paid minus the mortgage. So it's $46,288.21. So how much did they end up paying for the $175,000 house? Well, the $186,000 for the mortgage plus $35,000 for the down payment, so around $210,000 over 30 years. Okay, great. So for the couple in the previous problem, what's the unpaid balance after 10 years? What's the unpaid balance after 20 years? Well, how do you tell what the unpaid balance is? We're making a stream of payments. Right? So they're depositing money into the account. Payment size is that, $517.47. And they're making this stream of payments now. Well, after 10 years, they have 20 years left. So they're making 240 payments. So, how much could you borrow if you were making payments of this size for that long with I equals 0.02 divided by 12? right? So we're really thinking about how much could you afford to borrow to cover the house if this was your payments and this was the number of payments you had to make. So to figure out what the unpaid balance is after 10 years, we take their payment size and just plug it into the present value formula with I equal to the same thing. And now N is the number of payments that they have left to make. So it's 1 minus 1 plus 0.0166 to the minus 240 now, right? Note that this number has changed, over 0.0166 dot dot dot. And if you calculate that, the present value is, if it's 240, the present value turns out to be 102,290.38. So after 10 years, they've paid off about $38,000. Right? $140,000 is how much it was. They've paid off, they have this much left to pay off, and so how much is the total? $37,709.62. Note that a third of 140,000 is about 45,000, 46,000. So a third of the way through the mortgage, they've paid off less than a third of the mortgage, right? The first third of a any kind of loan that you're paying back interest, and it's only towards the end of the loan that you start building up more equity. So how much do they have left to pay after 10 years? After 20 years? Well, they have 10 times 12 equals 120 payments left. So what's the present value of, was that $517.47? That's our payment, times 1 minus 1 plus I to the minus now 120, right? Because it's only 120 payments left, over I. So after 20 years, they have 56,238.51 left to pay off. So after 2/3, they have a little more than a third left to pay off, and then they will own their house free and clear. Okay, so an amortization problem. So problems 33, 34, and 35. Amortization comes from the Latin mortire, which is to kill or to die, and amortization is, to kill off. So amortizing a loan means to kill it off, or essentially to pay it back. So an amortization table is a balance sheet, like we did for future value models. So for the couple in the previous examples, construct an amortization table. We know what the payment is. It's 517.47. We know what the interest rate per period was. That was 0.0166 dot dot dot. And we knew how much they owed. The present value, that's 140,000. Great. So we set up a table. Payment number. Back before this thing was called a hashtag, it was the symbol for number. Payment, interest, balance reduction, and balance. Okay. So before you've made any payments, you're starting with a balance of $140,000 that you owe. or they owe. So then they make their first payment. Payment 1. That's $517.47. How much interest do they owe? Well, the balance is $140,000. That's the interest rate. So balance times interest is how much interest is owed. That's $233.34. So out of this payment, this much goes to interest. So the rest of it goes to the balance reduction. So I take payment minus interest, and that gives me $284.13. So this amount of money goes to reducing the balance. So then I subtract this from that, and that gives me 715.90. No, it should be 0.87. My computer rounded on the... Okay. So, this is the balance. You make this payment. Some of the payment goes to paying off the interest. The interest you can calculate by taking the interest rate times whatever the balance is. And so that much of the payment has to go to paying off the interest. The rest, right, this minus this is the rest of the payment. That goes to paying off the debt. And so 140,000 minus 284.13 is this. So payment number 2, you pay $517.47. How much is the interest? Well, now this is the balance. So balance times interest is $232.86. So that's how much of your payment goes to interest. Note your interest load has gone down by, I don't know, 50 cents here, because the balance has gone down a little bit, and that means that you can pay more off on the debt. So you pay off an extra 50 cents. And so you end up with 139.431. I think my computer rounded everything to one decimal, so we'll just have to live with that. The number's a little bit out of whack. Great. So what about the third payment? Well, third payment is the same, right? How much of that goes to interest? Take this number, the balance, times the interest per period, and you can calculate those two, and it's 232.39. So that goes to interest. How much goes to paying off your debt? 285.08. So a little less than half of your payments at the beginning of the loan are going off to pay off interest rather than going off to pay the balance. And so then we're down to 146.20. Great. So note that they've made 3 payments of 500 and some, and they've managed to pay off about $1,000. Right? 140,000 down to 139,000. And that's 146. There we go. So payment 4, 517.47. You begin to see how this goes. Take the balance times the interest. That gives you the new interest, which is 231.92. And your balance reduction, this minus this, that goes to paying off your debt, and that's 285.55. And that gives you a total of 138,860.60. And then we can do 5 and 6, same payment. The interest is 231.44. Balance reduction is the rest of that payment, 286.03, and now we're left with 138,574.60. And then the last of the 6 payments. And interest again is this times the interest, and that gives you 230.96. And this minus this, the payment minus how much goes to interest is what goes to paying off the debt, and so then we subtract that from the balance to get the new balance, 138,288.10. Great. So how much have they paid over the first 6 payments? Well, 6 payments is $3,104.82. So that's how much they paid. How much have they paid in interest? $1,392.91. Right? And how much have they paid off on their debt, 1711.91. So they paid off more than they paid in interest, but not by a whole lot. That's the thing to keep in mind. When you're borrowing money, you pay off more money. You pay off the interest at the beginning, and then you build up equity in the second half. Okay, and there's some problems that are sort of future value and present value combined. From the previous worksheet, we had from example 4 in video 13, not previous worksheet, but previous video. Carl put away $1,000 every month after he starts working at age 25, and we found out that he could retire at age 75 after about 50 years with $1 million in the account. Suppose he lives until he's 92. How much can he take out of the account each month so that he dies with $0 in the account? Well, again, this is a present value problem because we have a pile of money and we're taking, he gets a pile of money in the present and he's taking money out of it. And so, you know, a loan is sort of like that. The bank gives you a pile of money and you have to pay, you know, you pay off the loan from that pile of money. So, payment, present value, payment 1 minus 1 plus I to the minus n over I. He starts with $1 million. Payment, we don't know what that is. I is 2% monthly, so 0.02 divided by 12. That's still this 0.0166 dot dot dot. And n now, well, if you're living from 75 to 92, that's 17 years times 12. And so n is 204. Plug everything in. 1 million equals payment, which we don't know, 1 minus 1 plus 0.0166 dot 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 to the minus 204 all over 0.0166 dot dot dot. Right. So calculate this fraction, divide a million by that fraction, and you get your payment is, oh, where is it? $5,786.47. So that's what, 67,000 a year maybe? So Carl can live pretty well for those last 17 years. Okay, so suppose Carl decides that, you know, he can get by on $4,000 a month. And so let's assume that he starts saving $1,000 per month at age 25. Assume that he dies at 92. This is after retirement. Right? He doesn't need the full $5,000 that he got before. And then his account still pays 2% interest compounded monthly. At what age can he retire? So this is a little bit of a trickier problem. We know that future value equals payment times 1 plus I to the n minus 1 over I. And so, to the n. For this problem, what do we know? He is going to put away money, $1,000 a month, and he's going to do it at 0.016 dot dot dot. Well, this is still this 2% interest compounded monthly. We don't know how long it's going to be, and we don't know how much money will be left. So he puts money away, and it gets up to a certain amount, and then he starts withdrawing from it. And then it turns into a present value problem. And I'm going to call this M because the number of months that he pays into the account is probably not the same as the number of months he pays out of the account. So M is the number of months that he would be in retirement, and the present value is what? We don't know. So what's going on here? He pays into the account n times while he's still working. He draws out of the account m times while he's retired. And we don't know what n and m is, or future value and present value. We do know two things, though. One, future value is the present value, right? Because in this problem, he starts putting money away, and it piles up and up and up and up, and then he retires. And then the pile of money that he has is the future value. And now we shift to the present value problem. He takes that same pile of money and he spends it down. So the future value in this problem is the present value in that problem. And the second thing is we're making kind of an unrealistic assumption. Is that the years involved here, he's going to work from 25 and die at 92. So that's 67 years. So we don't know the future value, the present value, and we don't know the times, but we do know that, it's not 108, sorry, 67 times 12 is 804. There's 804 months between starting to save at 25 and dying at 92. Okay, so what can we do here? Well, set future value equal to present value. Future value is 1,000 times 1 plus I. Oops. Well, we'll just leave it as I because that 0.0166 is a little pain to rewrite. Minus 1 over I equals 4,000. 1 minus 1 plus I to the minus m over I. And so we'll try and clean this out a little bit. We can cancel out the thousands. We can cancel out the I in the bottom. And we've got 1 plus I to the n minus 1 equals 4 minus 4 times 1 plus I to the minus m. Great. So if I add a 1 to both sides and move this term over to the other side, 1 plus I to the n plus 4 times 1 plus I to the minus m equals 5. Okay. And then finally, we can rewrite this like this, move that minus exponent down into the bottom, and we get that. And so we can then multiply through now by 1 plus I to the m on both sides to clear out the denominator. Excellent. So what do we get? 1 plus I to the m plus n plus 4 equals 5 to the 1 plus I to the m. But fortunately, we know that n plus m is 804. Do I have any space left down here? Nope, I don't. So if you grind this all out, you get 1 plus I to the m equals 1.562 ... So take log of both sides, we get m equals log of 1.562 ... over log of 1 plus I, and so that is 269 months, which is 22 years and 5 months. That's how much time he spends retired. He can retire at 70 if he's willing to live on $4,000 a year and a month instead of $5,000 a year. So if he waited till his account got to $1 million, he would wait till he's 75, and then he could retire and he'd get $5,500 a month. if he retires at 70, he'll get $4,000 a month until he dies at 92. And so that's one way to go about doing sort of financial planning, right? If you know when you're going to die, but you can make some estimates about when you might want to die, and think you can do this kind of a problem to figure out, how much you can start putting away now so that you can retire when you want. Okay, so oops, we have to do something before we get to the bonus video. Solving finance problems. Now, when it comes to the test or the quiz or whatever, well, certainly there's a test in the test 2 in the final. There'll be problems given to you, and you won't be told what kind of a problem it is, and you have to be able to tell what kind of problem it is so you can use the formula. So there are really 5 types: present value, future value, compound interest, present value, future value, compound interest, continuously compounded interest, continuously compounded interest, and simple interest. Those are the 5 types. How do you tell them apart? Well, first question: is there a stream of payments? That's the first question to ask yourself when you are looking at a finance problems. If yes, well, if there's a stream of payment, it's either a present value problem, which is usually paying back a loan or drawing down an account, something like that, or it's a future value problem, which is paying, well, saving for something. So present value means you've got a pile of money in the present and you're taking money out. Future value means that you're saving for money, so you have a pile of money in the future. If no stream of payments, well, then it's some kind of interest problem. If it contains the word continuously, well, and then it's a continuously compounded interest problem. If it says compounded, well, some kind of time term, so compounded daily, monthly, quarterly, weekly, etc., then this is just compound interest. If interest is not compounded, then it's just simple interest. APY problems are always one of these 2. They're either continuously compounded or compounded, right? And again, to check for an APY problem, you just put in $100 into the account for 1 year and see how much interest you got. Okay, so now derivation, what everybody's been waiting for, of the present value formula. Okay, so the idea here is you have to make payments sometime in the future. So how much do you have to put away now to be able to save for that payment? So recall the compound interest formula. Right? A equals P1 plus I to the n. So you have to make a first payment. So how much do you have to be able to have put away now to save for that? So suppose it's January, you have a payment due at the end of January. So how much do you have to put into your bank account now so that you will have that at the end of January? Well, you want to have I think I'm getting my numbers screwed up a little bit. Oh, no, I'm okay. So you want to have the payment at the end of the month, end of 1 month. So how much do you need to put away? What does P have to be so that you have payment at the end of 1 month? Well, you have to put away this much to be able to afford that. And so how much do you have to put away now to be able to afford the second payment? Well, the second payment is due in 2 months, right? So n equals 2. And so to get A equal to PMT after 2 months, you need the payment divided by 1 plus I squared. And likewise, so what is this? This is the amount of money you put away now to okay, that's a little bit weird. Amount of money you put away now to have in 2 months. And so if you need a payment of $500, maybe you only need to put away $480, and in 2 months you'll the interest will catch up to it. So dot 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 dot. To get to the nth payment, you need this much money. Okay, great. So how much can you borrow? Well, if this money is the amount that you can save to get the payments, so the present value is P1 plus P2 plus dot 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 plus Pn. And now we're going to just grind through that formula a little bit. Right? Present value is payment. If I factor the payment out of all those things, it's 1 over 1 plus I plus 1 plus 1 over I plus 1 squared plus dot 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 plus 1 over I plus n 1 over 1 plus I raised to the n, like that. Great. So to simplify my life a little bit, I'll factor out one of these guys. So payment over I plus 1 is 1 plus 1 over 1 plus I squared plus dot dot dot. Well, we'll put in a little bit more than just dot dot dot. So that should be 1 plus 1 over 1 plus I cubed plus dot 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 plus 1 over I plus 1 to the n minus 1, and this is n minus 1 because we took one of those out. So present value is payment over 1 plus I. And now we're going to use the same trick we did last time. This whole thing, remember that 1 plus x squared plus dot 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 plus x to the n minus 1 is x to the n minus 1 over x minus 1. So using this thing, 1 over 1 plus I is x, we can rewrite this whole parentheses here as that. So 1 over 1 plus I to the n minus 1 over 1 over 1 plus I minus 1. Awesome. So we're almost done. So what can we do with this? Well, we can simplify our life a little bit by leaving the payment as it is out front. In the numerator, let me rewrite this as 1 plus I to the minus n. That's this term, minus 1. And then 1 plus I times all this. Well, 1 plus I times 1 over 1 plus I is 1. 1 plus I times 1 times minus 1 is minus 1 minus I. So present value is payment 1 plus I to the minus n minus 1 all over 1 minus 1 minus I. And then I'll take the minus sign up top and multiply it through up here, and we get our present value formula.